have something pretty cool for you today. We're going to look at a mathematical technique called Markov chains. And you would see it in a class actually, but it wouldn't be for a while. You'd have to go quite a ways in your mathematical training before you would see these. And I think it's kind of a shame because they're actually pretty cool. And I'm going to show you a real streamlined version of these that anybody can follow along and see what happens with these. And it's kind of cool because they let you predict the future of certain situations. So what I'm going to do is we're going to make up a hypothetical situation. I'll put a little note on my math cam here of what's going to happen. But the idea is we're going to look at a situation where we have a bunch of subscribers to high-speed internet, and some are on cable internet and some are on DSL. And similar to a choice you would have if you want to pay for high-speed internet. And what we're going to look at is how people might switch back and forth between the two systems, and can we predict what's going to happen over time. So I made up a hypothetical city here. Let's say we have, just to make things nice for us, let's say we have a city of 100,000 people. And for this particular example, I know you can't read that, I'll make it a little bigger for you. Let's say that everybody in the whole city subscribes to either cable internet or DSL internet, just to make things simple. So let's say out of all these people, let's say out of the cable people we have 56,000 people, and then on the DSL rather, the remainder, that would be 44,000. All right, so just to make things interesting, let's say hypothetically that every month the cable and the DSL people observe that some of the people switch from one system to the other. So let's say every month, I made up some percentages just to make things kind of nice with the numbers. Let's say every month 10% of cable switches to DSL. So we're going to have 10% of cable, they go to DSL. The other 90% are happy with their cable internet and they stick with it. And let's say at the same time every month 15% of the DSL people end up switching to cable. So every month you have kind of this turnover going on where people switch back and forth. So what I would like you to do is predict what's going to happen next month. Predict how many cable subscribers you will have and how many DSL. And it's not that hard to do for next month. You just have to count the percentages. And for instance, you want to look at how many people stayed with cable and how many came from the DSL side. So for example, let's say for cable, well, if 10% are going to jump ship, then you're going to keep 90%. So next month we could say, all right, you have 90%, that's 0.90, of the 56,000 are going to stay with cable. And we could add how many are going to come from DSL. Well, I know that 15% of my DSL subscribers, that was 44,000, are going to come over and become cable subscribers. So here's how I compute how many cable subscribers we have. And I went ahead and did this ahead of time. This comes out to be 57,000 even. So it looks like the cable system gained 1,000 people that month. Even though they lost some and they gained some, but overall they gained 1,000. And you could do the same thing for the DSL people. In fact, the DSL, they're going to keep 85% of their current subscribers, which is 44,000. And they're going to actually get 10% from the cable folks. That was 56,000. And I did this ahead of time. This comes out to be 43,000 even. So they lost 1,000 subscribers. All right, so what I really want to know is what's going to happen month after month after month. And it's interesting what happens with the trends. And the problem is it gets a little tedious to compute. So there's a nice organizing way of doing this, and it's using these mathematical devices called matrices. Now you might have done these in a class, maybe, look at a matrix. And I don't want you to think you have to know anything about a matrix for now. All you have to know for now is it's a grid of numbers. So I'm going to make a little grid of numbers, and I'll show you what I'm putting in here and why, and then I'll show you why this actually works. And then I got some cool stuff on my calculator I'll show you with what happens with these guys. So what we're going to do first is we're going to make what's called a transition matrix. And what this does is it measures the percentages of who changes to what. So I'm going to make a little grid. So I'll make a little, usually they put them in brackets, so I'll make a little grid of numbers here. And what's going to happen is I'll have cable first, and then DSL. And I'm going to do this on both the rows and the columns. And on the left, on these rows here, this is going to be the before, and then we're going to have after here. So in other words, I want to know what percentage of people were cable before and they're cable after. In other words, they stayed with our cable internet, and that was 90%. So I'm going to put 0.90 in here. Now, how many switched to DSL? Well, from cable to DSL, we talked about 10% of the people are going to actually switch. This little entry here, how many people switched from DSL to cable, and that was 15. And finally, how many people just stick with their DSL, and that was the remainder, which is 85. So all we've really done is made a little organized grid of the numbers, the percentages we're talking about. Well, in addition to that, I'm going to make a single little row matrix of the people I have right now in my city. So I'll put cable first, and then we'll put DSL. And we talked about 56,000 cable subscribers and 44,000 DSL. Well, what we're going to do is we're going to multiply these matrices. Now that's a whole fancy thing you might learn in a class, but that's okay. I'm going to show you how this one works. So I'm going to actually think of these as mathematical objects, and we're going to multiply these two guys. And all I want you to observe with me, so it doesn't matter if you don't know a thing about matrices. What I want you to watch is how these things multiply, and I don't know, maybe decide why would this make sense, because it's going to seem a little strange at first. The way these multiply, this is going to create a new little row here, a new little matrix. And the way it works is you take the whole row from the first matrix, and you match it up to the whole row of this, or the first column of the second matrix, and you line these up. So you align the 56,000 with the 0.90 and the 44,000 with the 0.15, and you multiply those pairs, and then you total it up. And that's the number that goes here. So if you look at that, it sounds kind of like a crazy way to multiply things, I know, but I'm going to show you why this actually does something good for you. If you do this, what we're going to do is we're going to take 56,000, join it with the 0.90, multiply those together, 56,000 times 0.90. Do the same thing with the other two guys, so we have 44,000 and the 0.15, multiply those as pairs and add them up. And that's the number that's going to go in here. Well, look what you are really doing. In fact, that's the same exact computation we did a minute ago. That was exactly how many people are subscribing to cable right now. So that's going to give you your 57,000 for the cable. And we will do a similar thing with the second one. We'll do this row by this column, match them up again, total them up, and you're going to get 44,000 here, which means that's exactly how many DSL subscribers you have. So all we really did was the same computation in just sort of this organized way. Well, you might say, okay, so what? What's the good of that? Well, the good of that is this is a standard kind of multiplication, and gadgets know it, computers know it. In fact, my little graphing calculator knows it. So what I could do is enter these in my calculator and have the calculator do the work. So for instance, I have with me a Texas Instruments TI-84, and I know a lot of students on our campus have the same calculators. So this is going to look just like what you would do on your own calculator. I have actually entered these matrices in ahead of time. So for example, I have the matrix A in there, and I'll show you on my calculator. It looks just like what you would see on my piece of paper. And here's B, for instance. This was our transition matrix, and there are those exact same numbers. And what I can do is I can actually multiply these guys, have my calculator do it, and lo and behold, it gives me the exact same result. All right, so what? I had my calculator do it. Well, the real advantage is if you want to see what's going to happen 2 months down the line, what it boils down to is taking your previous answer here and throwing it back in the same matrix. But the way we're going to do it is we're just going to do this matrix twice. So it's kind of like you get to do standard arithmetic with it. And I called this one A and this one B, and that means on my calculator, all I have to do is say, all right, do the same thing, but this time do B twice. In other words, square it. That's what's going to happen 2 months from now. If you want to see 3 months from now, I'll just take that matrix and do it cubed. And my calculator can keep computing all these things. Now, that still can get a little tedious, I suppose, so I went ahead and did it ahead of time. I'm going to show you what happens. This is the interesting part. I did these numbers ahead of time on my calculator, and I wrote them down for you. I know it's a little small, so I'll zoom in on this. So I just find the same matrices we just talked about, and I started doing the B matrix more and more times, and these are the numbers of cable and DSL subscribers. Now watch what happens. These numbers keep changing. They keep exchanging subscribers back and forth, but by the time I get to the 10th month, there you see A times B to the 10th. Well, it's getting like sort of settled down. I mean, the numbers are kind of zeroing in on a certain value, and in fact, I kept going. I started skipping some now. I got to the 20th, the 30th, the 40th, and the 50th, and look what happens. They have actually zeroed in and settled down on 60,000 and 40,000. So if this trend remained where the same percentage of people switched back and forth, this would actually settle into this equilibrium where even though they're exchanging people every month, you always have 60,000 cable subscribers and 40,000 DSL forever afterwards. Here's an even weirder part. I did it again, but this time I made up a different city. And this time I said, okay, let's pretend that my city has only 5,000 cable subscribers and 95,000 DSL. What do you think it would settle down to? Well, I did it all again, and we went through the list, and you see these numbers start to change. I mean, the 5,000 jumped pretty quick up to 18 and then 29. It kept jumping up. But I went all down this list, and when I got to the end, guess what happened? I got to the same equilibrium numbers. So in other words, it didn't matter how many you start with. Eventually, if you give it enough time, if this trend continued, you would always have 60,000 cable and 40,000 DSL. One more weird observation, or cool observation. You can actually tell what's going to happen in the future if this trend remains by simply looking at the transition matrix. So one last time what I did was I took the matrix itself, just that matrix of the percentages, and I started taking powers of it. So not multiplying, just powers of it, and watch what happens. As I go down this list, all these percentages start adjusting. And these are the percentages you would get month after month. But eventually, here's 10, 20, 30, and finally 40 months. Eventually what you see is the percentages themselves have settled down. And you see 60% and 40% on both of those columns. So 60 and 40, 60 and 40, that tells you over time, that's exactly what's going to happen no matter what you start with. You're going to have 60% on cable, 40% on DSL. So they use these to predict lots of things. Like you can do them with more than two things, by the way. You can have the matrix as big as you want. You can talk about, voting Democrat or Republican or Independent and how the three trade around each year or things like that. And you can see if the trends maintain, what's going to happen 10 years out. It's pretty cool. It actually is used by researchers in the real world to try and predict the future. How accurate is it? Well, it depends if the trends remain.
Mathman Dan here. We're checking out some areas where mathematics shows up in the real world. Right now I'm standing, well, almost in the ocean in Carlsbad, California. And it turns out there's lots of math that goes into the study of the oceans. There are some simple examples like there's an algebraic formula that'll tell you how the pressure changes as you dive deeper, for example. There are lots of examples of higher mathematics. For instance, if you're in an algebra class, you'll learn about functions of a variable like x. Well, lots of things that you study require more than one input variable. So for example, one thing they study is the salinity of the ocean. That depends on 4 input variables, not just one. You need your latitude, your longitude, your depth, and also the time. If you input those 4 things, it will determine one particular salinity, but it requires that many inputs to study that. Now that would take you to a 3rd semester calculus class to actually start studying those things. Now they've been studying the ocean for hundreds of years. A big field of study right now is what's called fluid dynamics, and this is the actual motion of water itself. It's very difficult to study because on the one hand you're looking at things at an inch level of movement, and another thing you're looking at thousands of miles of like the Gulf Stream of ocean water moving. So there's some very sophisticated mathematics that goes into this. One of the areas is called partial differential equations. You would learn about that after some calculus classes. Those, unfortunately, are often very difficult to solve. So there are some whole other areas of mathematics, such as linear algebra or numerical analysis, that they use to try and come up with approximate solutions to these things. So why are they looking at this so carefully? Well, the movement of water in the ocean, both at the small scale and the large scale, has a lot to do with our climate. And you can imagine with all the hurricanes we've had lately and all the temperature changes, the ocean has a lot to tell us about that. They've been studying it for a long time, and they still have a long way to go to figure things out completely. For instance, if you drop off a volleyball somewhere in the middle of the ocean, do you have any idea where it's going to end up? Probably not. Hard to predict, right? Well, they're working on things like that, trying to create mathematical systems to look at it. Another thing you can look at, of course, is the waves themselves. If you think about the ocean waves, it's not really the water moving out so much, it's the water levels changing in a certain rhythm. Well, back in the studio, I'm going to show you some pictures of what waves do, and you'll see this has a lot to do with some functions you might have seen if you've had a trigonometry class, actually. Back in the studio, I'll show you those details.
Well, that wasn't a bad day. But anyway, I mentioned several different areas of mathematics that get applied to this, and some of them are pretty heavy duty. The study of the ocean water is related to fluid dynamics or fluid flow, and it's an ongoing problem to this day that there's always research being done because it's a very complicated problem. And one of the things you can look at involve partial differential equations. And you wouldn't see those, for a long time in your math classes. But we're not going to do those because they're a little crazy. But just to scare you, I have them on my screen, and you can see what they look like. So if you want to try and look at here, I'll try and blow them up a little bit. If you want to try and tackle those, that's what you'd have to work on. Now, it turns out, these equations are not solvable as we know yet. So this is a huge ongoing problem. In fact, there is an organization that will give you $1 million if you can prove that they're solvable in a nice way. So, it could be a little riches in your future if you work on this. But what they do try and work on is having computers estimate or simulate possible solutions to these. So for example, here's one shot of computer program working on these, and you can see that these are all models done off the equations, and so they're trying to basically make math describe how the little turns and eddies in the water that can happen, turbulence, and it can get pretty crazy. And this is studied in the ocean along with other parts where deeper in the ocean the water behaves differently as it does on the surface, as it does near the coast, as it does out in the middle. So there's all kinds of different aspects for them to worry about. So I was just going to show you one little aspect that's maybe a little easier to follow, and that is the shape of waves themselves. And I hinted that this was related to maybe something you'd see in a trig class. So what I'm going to show you, this is an example of, well, this is a standard old sine wave actually. I have it moving. This is sort of simulating what the shapes of waves might do. And if you've had a trig class, I'll show you in a second where this graph comes from, but if you've had a trig class, this is one of those basic trigonometric functions you will study. And this really is kind of simulating what a wave does. And one interesting thing to point out is that the water is not really moving left to right. It's really just rising up and down in place, and it's just the shape of the surface that's moving. It sort of has the illusion of water moving. Really, the water's just kind of moving up and down. It's almost like if you watch, the surfers paddling out at the beach, they can just ride over the waves when they're not ready to stand up and ride the waves in. So if they're just paddling out, you'll see the wave just, kind of bump them up and they'll go back down. They don't really move, with the water. It's just the water's flowing up and down, and the shape itself is moving, what they end up riding later. Another thing, if you ever seen people in the ball game, the stadium do the wave, well, the wave is the motion of the people standing up and sitting down, right? The people aren't really moving. It's just they're changing position and makes it appear like a shape in moving around. Same idea. So anyway, these sine waves, they're actually linked to circles. And I was going to show you, I have an example here of how this comes about. So what I want you to watch in this little example is there's a circle on the left, and I want you to imagine it's like a Ferris wheel, and you're going to take a ride. And there's going to be a dot that goes around that circle, and on the right, there's going to be a graph formed from just the height of the dot. So you've got circular going on the left there, and then on the right you're going to see a graph of the height. So watch it closely. This is where the sine wave comes from. And there's going to be some tie-ins with circles, so that's why I wanted you to pay attention to this. So here's one waveform, if you will. Okay, so there's our basic shape. Well, it turns out waves are kind of like this, but they're actually a little closer to another related shape. So I'm going to show you this one now. This is I don't know if you can see the difference. In purple, I have the same old sine wave, and then in blue on top of it, I have this other shape called a trochoid. Trochoid. And it's a little bit different shape. I'll show you where it comes from. It's actually from, imagine if you're riding a bike and you had a light on your spokes. Not on the edge of the wheel, but on your spokes. And imagine the trail it would leave. So we're going to look at an animation here of what it might look like if you were riding along. So look, watch carefully. This is going to go a little fast. Okay, I'll try and slow it down. That's your bicycle wheel, and there's a little light on the spoke, and then when we go, it's going to leave this path. So it looks kind of like some arches. It turns out this is actually closer to the real shape of these waves in the ocean as compared to the sine wave, but they're similar. So there's these waveforms. They're formed by the surface, not by the water moving, actually. Now, so here's another example, right? There's a both formed from circles. So I have a nice animation I'm going to show you where it actually tries to show you what happens with the water itself. So this is a wave. What you're going to see, there's a wave that's going to flow by, and then there's going to be little drawings of particles sitting in the ocean, like what a little part of the water would actually be doing. What you want you to notice is it doesn't actually shift left or right much, a little bit. Mostly what it does is go up and down in little circular motions. So it would actually make perfect sense that these functions from trig class, which are actually formed by circles rolling around or watching the height around a rolling circle, would actually come into play with the shapes of these waves. So here we go. Watch closely. There's some particles there. I'm going to scoot it down, make a little room for you, and it's tracing the path of them. And you can see they actually form little circles, and they are moving a little bit. You'll notice they move more on the top than they do near the bottom. The bottom, they're staying pretty much in place while they draw these little spirals. So that's what's going on. If you watch a buoy floating in the water out, in the ocean sometime, you'll see the waves drift by it, and the buoy goes up and down. I know the buoy's anchored, but it really wouldn't drift that much, even if it weren't, because that's just not the way the motion is going. All right, so next time you go to the beach, I want you to pay attention because there's a lot of math going on. That's just one simple thing. A couple weeks ago, I was going to say, well, it was actually last season, we actually talked about the tides. And again, some more functions from trig class showed up. So lots of stuff to look at if you decide to go to the ocean.
Hi, I'm Mathman Dan. We are out in the field today. We're going to show you a little bit about how some math shows up in the real world. We're actually a little outside of Temecula in Riverside County, and behind me is Lake Skinner. And this lake is the result of, in the 70s, they built a dam that you can see at the far end of the lake over there. That dam's about almost a mile across and about 100 feet tall. So, you know, there's a lot of engineering and physics and math that goes into building a dam like that. But one of the things we can look at is they need to figure out how much force is actually pushing on that wall down there to know how thick to make it and how strong to make it. Well, this is actually a little trickier than you might think, because the problem is, actually the force doesn't have anything to do with how wide the dam is. It all has to do with how deep the dam is. So if you ever go swimming in a lake or a swimming pool, you might notice it actually gets more pressure on you as you go deeper, and that's the whole issue. So unfortunately, I can't just measure how big the dam is and multiply it by some number, because every point on that dam is getting a different amount of pressure on it. Every inch you go deeper gets more and more pressure. So to actually get a really relatively accurate measurement is a little tricky, but it turns out there's some good mathematical techniques, and in fact, if you've had a little calculus, we can actually get to an exact number, as long as we can recreate a formula that'll tell us how wide the dam is at any given depth. So if we can do that, tell you you go 10 feet deep, here's how wide the dam is at that point, we can actually create a way to make an estimate, and calculus has a way of making those estimates into an exact value. And that part I will show you back at the studio. So when we were out at Lake Skinner, we're looking at this dam, and I mentioned that, actually I think I slightly misspoke. I think I said once that the force doesn't matter how wide the dam is. That's not true. The force does matter how large the dam is. The pressure doesn't matter how wide the dam is. And that's kind of weird to think about. I mean, the idea is that you have this huge lake pushing on this dam, and you would think that it would somehow affect the pressure, and it turns out it really doesn't. All that depends on the pressure is how deep you are underwater. So for instance, if you're swimming 10 feet underwater in a swimming pool in someone's backyard, and you're swimming 10 feet underwater in a lake like Lake Skinner, you feel the same pressure. It doesn't matter how much water is around you, it only matters how deep you are. So that's one key we're going to look at. So what we're going to talk about is how strong does that dam have to be, and I'm going to give you guys a way to estimate how much force is pushing on that dam, which would tell you how strong that dam needs to be to push back so it doesn't get pushed over by all that water. So, it's a difficult thing because, as I mentioned, the deeper you go, the more pressure you get, and that changes every inch you go. So the challenge is, how do you find the total pressure, or the total force rather, if it's changing everywhere? So I'm going to show you a little strategy how we could estimate it, and then when we're done, I'll mention how you can actually use calculus if you want to be really precise. But we don't need to use calculus. We're just going to do some simple arithmetic here, and the strategy, though, is what I need to show you. So the first thing I need to explain to you before we get going is the pressure that you get from water all depends on how much water is over you, but the water pushes in all directions. So for instance, if you took a penny and you put it on the bottom of a swimming pool, the amount of pressure or force pushing on that penny is simply how much weight of the water is over the penny. So you can imagine taking just the water exactly over the penny. If you can figure out how much that water weighs, that's the force the penny's going to feel from the water. But the thing is, that force is the same if you take the penny and flip it sideways, right? The force doesn't go away just because you made the penny look, thinner from looking above down at it. So it doesn't matter how things are oriented. The idea is the force is how much weight of the water is over it, no matter how you turn or rotate the object. So what we're going to do, I've drawn the dam, well, I've drawn a sample dam on my screen here. I don't know the exact shape of the dam at Lake Skinner, but we'll pretend this is the approximate dam here. And what we're going to do as a strategy is I'm going to pick a certain location of the dam. And remember, the pressure is changing at every depth we go. So I'm going to pick a segment here, and I'm just going to draw you a horizontal segment approximately. That's a little squiggly. You're going to pretend that's a nice horizontal segment. And you could pick this anywhere on the dam. Let's just say we only made this 6 inches high, so let's say. So this is only going to be a ½ foot tall. Okay, so if that's a ½ foot tall, well, let's say it's about, the dam is about 100 feet tall overall. So let's say, I don't pick this near the bottom. Let's make this about 80 feet here. So let's say it's 80 feet below the surface, approximately. And the strategy is, I know I made it a ½ foot tall, and technically there's more pressure at the bottom of that 6 inches than there are at the top, than there is at the top. But since it's so small compared to the overall height of the thing, let's just say we're going to round a little bit, and we'll say it's approximately the same kind of pressure all throughout this whole strip. So we'll say the strip's all at the same depth, 80 feet, even though, of course, it is a few inches off up and down. And then let's see, we need to know how wide the strip is, and the dam actually is almost a mile long. Well, a mile's 5,280 feet. Let's just say this one is, we'll make it 5,000 feet just to keep the numbers nice.
So here's the funny part. I want you to take this strip on the dam. I want you to imagine if you're gonna cut the concrete right out of this thing. You're gonna take this, like a strip here, and you're gonna cut it out of the dam, and you're gonna lay it flat at that same depth. So what I'm gonna do is I'm gonna draw that thing on its side, basically. We're gonna cut that strip out, and I'm gonna imagine it laying down. So imagine this underwater, and what I want you guys to help me do is figure out how much water is directly over this thing. So imagine making a rectangular block out of this. This is going to be like a column of water, if you will. I don't know. Imagine the water suspended in midair somehow or frozen or something. So you have a big rectangular brick of water. And if you were watching all my measurements, this isn't too hard to measure. It was 5,000 feet on the length here. It was 80 feet of water above you, so that's how tall this column of water is. And the little width here was, we just said it was a ½ foot. That's how much we cut out before I laid it down. All right, what I'd like you to do next is see if you can help me figure out the volume of the water. And once we know the volume, then we can actually figure out the height. So let's see, the volume of water, let's make that, well, it's just a rectangular block, right? So it's length times width times height. I try to make the numbers not too bad. So length is 5,000. The height, or the width rather, is a half, and the height is 80. So if I compute this all out, I think I did this correctly. It's 200,000. All right, what are the units there? That is feet times feet times feet. So that is feet cubed. So next what I need you to do, this is a volume. I need you to next tell me how heavy this is. And water weighs quite a bit. Water weighs over 8 pounds per gallon. But I looked up how much it weighs for a cubic foot. And it turns out 1 cubic foot of water is about 62.5 pounds. So we're going to say 62.5, this is pounds per cubic foot, multiplied by all these cubic feet, 200,000 of them. That gives you approximately, and by the way, look at the units. The feet cubed are going to cancel, and you're left with pounds, which is exactly what I want. It's 12,500,000 pounds. Just a little bit, right? So this is how much water is weighing basically over this segment that we laid down. But remember, water pushes in all directions the same force. So this is how much force is pushing against our dam just on that strip. So if you wanted a good estimate, how would you figure out the total force on the dam? Well, you would do every strip all the way up the dam. So this one was at 80 feet. You do another one at like 80.5 feet, then another one at 81 feet, and etc. through the whole thing. That would be a little bit tedious, right? But if you did that, you would get a good estimate for how much force is pushing on that dam. So that estimate would be a little bit off. If you really wanted to be precise, and if you have had a little calculus, you can actually do this with an integral. And the idea from calculus is you do the exact same computation we did, but you would do it a little more generically. So instead of saying a ½ foot wide, for example, you would have your column, and you would say, you know, it's not a ½ foot wide, it's, usually they use a symbol like delta y wide, a little bit of height. Delta just means change. And then you make a formula for how far down it is. So for example, you wouldn't say it was 80 feet down, you would say it's, well, wherever you are at a certain height y, it'd be 100 minus that. So if you were 10 feet up, it'd be 100 minus 10, it'd be 90 feet of water over you. And then you'd make a formula for how wide it is, because that changes depending on where you are in the dam. And if you do that, you make the same computation we did. You can actually, with calculus, imagine doing 1,000 of these different strips, or then 1,000,000 or 1,000,000,000 or more and more and more. And calculus can actually figure out, even if you did an infinite number of strips that themselves got infinitely thin, and that's how you get the real answer. It's all based on a limit, and that turns into an integral, if that means anything to you. And if you ever do a problem like this in a calculus class, which you might in second semester calculus, this is the whole deal. You're just taking estimates, and you're making them more and more precise.